When you look up at the night sky on a clear evening far from city lights, you might notice a faint smudge of light in the constellation Andromeda. It doesn't look like much, just a pale blur among thousands of stars. Most people pass right over it without a second thought. But that tiny patch of light represents something so vast, so incomprehensibly massive, that your brain actively resists understanding its true scale. That smudge is the Andromeda Galaxy, and if you could see it as it truly exists, if your eyes could gather enough light to reveal its full extent, it would dominate your entire view of the heavens. It would stretch across an area of sky 6 times wider than the full moon. 6 times. The moon, that enormous glowing disk that seems to fill the night, would fit inside Andromeda's visible area 6 times over. But here's what makes this even more staggering. What you're seeing, that faint glow, barely visible to your naked eye, is the combined light of over 1 trillion stars. 1 trillion individual suns, each potentially hosting their own planets, their own systems, their own stories. And that light has been travelling towards you for 2.5 million years. When those photons began their journey, your ancestors were just beginning to walk upright on the African savanna. No cities existed, no agriculture, no written language, nothing recognisable as human civilization. Just early hominids learning to use primitive stone tools. And all that time, while humanity evolved from those distant ancestors into everything we've become, that light was crossing the void between galaxies, moving at the fastest speed possible in our universe, never stopping, never slowing, for 2.5 million years, just to reach your eyes tonight. This is Andromeda, the nearest major galaxy to our own, our cosmic neighbour. And understanding its true scale requires us to completely recalibrate our sense of what words like big or far actually mean. Because Andromeda isn't just large, it's not simply distant. It exists on a scale that makes almost everything in your daily experience, everything you consider vast or impressive, completely meaningless by comparison. The entire Earth, the planet that contains every human who has ever lived, every city, every ocean, every mountain range, is 12,742 kilometers across. That seems massive. It takes commercial aircraft hours to fly across continents. It takes months for ships to circumnavigate the globe. But Andromeda? Andromeda is 220,000 light-years in diameter. To put that in perspective, light travels at 290,792 kilometers per second. In 1 year, moving at that speed without ever stopping, light covers about 9.46 trillion kilometers. That's 1 light-year. Now multiply that by 220,000. The result is a number so large it becomes abstract. We're talking about 2.8 quintillion kilometers from one side of Andromeda to the other. That's 2,080,000 kilometers. If you tried to count to that number, saying 1 number per second, it would take you over 65 billion years. The universe itself is only 13.8 billion years old. You couldn't count that high even if you'd started at the Big Bang and never stopped. But raw numbers don't really help us grasp this scale. Our brains didn't evolve to comprehend distances measured in quintillions. So let's try something different. Let's shrink everything down to a scale we can actually visualize. Imagine the entire Milky Way galaxy. Our home galaxy containing somewhere between 200 and 400 billion stars, reduced to the size of a dinner plate. Just a regular plate, maybe 25 centimeters across. At that scale, our solar system, the Sun, and all its planets, everything from Mercury to Neptune would be smaller than a single atom on that plate. You couldn't see it with the most powerful microscope ever built. Earth would be so incomprehensibly tiny at this scale that describing it becomes impossible. Now, at this same scale, where our entire galaxy is just a dinner plate, how far away would Andromeda be? In the next room? Down the street? Across town? No. At this scale, Andromeda would be another dinner plate positioned about 6 meters away. 2 dinner plates, 6 meters apart. That's the distance between our galaxies when you shrink them down to comprehensible sizes. But here's what really matters. Those two plates are rushing toward each other. They're on a collision course, and there's nothing anyone can do to stop it. For most of human history, we didn't even know Andromeda was a galaxy. For centuries, astronomers classified it as a nebula, just another cloud of glowing gas somewhere in our own cosmic neighbourhood. It appeared in Persian astronomical texts as early as 964 CE, described by the astronomer Abd al-Rahman al-Sufi as a small cloud. Chinese astronomers also noted it, calling it various names but never understanding what they were actually observing. Even when telescopes became powerful enough to reveal structure in that pale smudge, astronomers still assumed it was part of the Milky Way, a cloud of gas and stars within our own galaxy, nothing more. This wasn't ignorance. It was the rational conclusion based on available evidence. The scale of the universe, the existence of other galaxies, these concepts simply didn't exist yet in human understanding. The entire cosmos, as far as anyone knew, consisted of one galaxy. Our galaxy. Everything visible in the night sky was presumed to be part of that single structure. The idea that other galaxies might exist, separate island universes, each containing billions or trillions of stars, seemed absurd, ridiculous, unnecessarily complicated. Then came Edwin Hubble. In 1924, using the 100-inch Hooker telescope at Mount Wilson Observatory in California, Hubble made observations that would completely transform humanity's understanding of the universe. He identified Cepheid variable stars in what was then called the Andromeda Nebula. These stars pulse with predictable brightness, and their pulsation rate directly correlates to their actual luminosity. By measuring how bright they appeared versus how bright they should be, Hubble could calculate their distance, and the numbers he got back were shocking. The Andromeda Nebula wasn't a cloud of gas within the Milky Way. It was nearly 1 million light-years away, far, far beyond the known boundaries of our galaxy. It wasn't a nebula at all. It was another galaxy entirely. A separate universe of stars. The implications were staggering. If Andromeda was a galaxy, then those other faint smudges visible through powerful telescopes, the ones catalogued as nebulae, they might be galaxies too. And they were. Suddenly, the universe expanded in human understanding from one galaxy to potentially billions. Overnight, our cosmic perspective shifted from thinking we lived in everything that existed to realizing we occupied just one galaxy among countless others scattered throughout an incomprehensibly vast cosmos. Modern measurements have refined Hubble's initial distance estimate. We now know Andromeda sits approximately 2.537 million light-years away. That light you see when you look at it tonight left Andromeda's stars during the Pleistocene epoch on Earth. Early humans were beginning to spread across continents. Saber-toothed cats and woolly mammoths still roamed the landscape. The last ice age was just beginning to tighten its grip on the planet. And in all that time, across all those millennia of evolutionary change and extinction, and continental drift, that light just travelled, moving through the absolute emptiness of intergalactic space at the maximum possible speed, crossing a void so vast that it contains almost nothing. No stars, no planets, no dust or gas or debris, just vacuum, punctuated occasionally by the odd hydrogen atom every few cubic meters, for 2.537 million years. But distance is only part of what makes Andromeda's scale so difficult to grasp. The real mind-breaking aspect is its physical size, its actual diameter. Because Andromeda isn't just far away, it's monumentally, almost absurdly massive. At 220,000 light-years across, Andromeda is more than twice the diameter of the Milky Way. Our galaxy, the one that contains our entire solar system plus somewhere between 200 and 400 billion other stars, is roughly 100,000 light-years in diameter. We think of the Milky Way as enormous, and it is. Crossing from one side to the other at light speed would take 100,000 years. but Andromeda makes our galaxy look almost modest by comparison. If you place them side by side, Andromeda would dwarf the Milky Way. It would stretch more than twice as far in every direction. That size difference becomes even more dramatic when you consider what that means in terms of volume. Volume increases with the cube of diameter. Since Andromeda is roughly 2.2 times wider than the Milky Way, its volume is approximately 10.6 times larger, 10 times more space. 10 times more territory. 10 times more room for stars and planets and nebulae and black holes and everything else that makes up a galaxy. And filling all that space are stars. So many stars that counting them becomes a futile exercise in trying to comprehend the incomprehensible. Current estimates suggest Andromeda contains approximately 1 trillion stars. 1 trillion. That's 1,000 individual stars. To put that in perspective, if you started counting right now, one number per second, never sleeping, never stopping, never taking a break, it would take you almost 32,000 years to count to 1 trillion. You could have started counting when the last ice age was at its peak, when woolly mammoths still existed, when humans lived in caves and you still wouldn't be finished counting today. And each of those trillion stars is a sun. Many are smaller than our sun. Many are larger. Some are red dwarfs, tiny dim stars that will burn for trillions of years. Others are blue giants, massive stellar furnaces burning so hot and bright they'll exhaust their fuel in just millions of years. Some are dying, expanding into red giants that will eventually shed their outer layers into space. Others are being born, coalescing from clouds of gas and dust in stellar nurseries scattered throughout the galaxy. Every single one represents a point of light, a nuclear furnace fusing hydrogen into helium, generating the energy that makes galaxies visible across intergalactic distances. Now here's where it gets truly difficult to process. If Andromeda has roughly 1 trillion stars, and a significant percentage of those stars probably host planetary systems, how many planets might exist in that galaxy? Conservative estimates based on what we've learned from our own galaxy suggest that most stars have at least one planet. Let's be extremely conservative and say only half of Andromeda's stars have planets. That's 500 billion planetary systems. If each system averages just 2 planets, we're talking about 1 trillion planets. 1 trillion worlds, rocky planets like Earth, gas giants like Jupiter, ice worlds, lava worlds, ocean worlds, desert worlds, worlds with thick atmospheres, worlds with no atmospheres at all, worlds orbiting close to their stars baked by intense radiation, worlds in the outer reaches of their systems frozen in perpetual darkness. And among those trillion planets, how many might harbour life? We don't know. We can't even begin to estimate with any real confidence. But even if life is extraordinarily rare, even if only 1 in a billion planets develops life, that still means 1,000 living worlds in Andromeda alone. 1,000 planets where biology has emerged, where evolution has occurred, where complexity has arisen from simplicity. And if intelligent life is even rarer, say 1 in a trillion planets, there could still be 1 or more technological civilizations in Andromeda right now, looking out at the universe, wondering if they're alone, perhaps even looking at our galaxy, the Milky Way, seeing it as we see Andromeda, a faint smudge of light in their night sky. The mass contained in all those stars, all that matter compressed into one cosmic structure, is equally staggering. Andromeda's total mass is estimated at approximately 1.5 trillion solar masses. 1 solar mass equals the mass of our Sun, which itself weighs about 2 × 1030 kilograms. Multiply that by 1.5 trillion, and you get a number so large it becomes meaningless. We're talking about 3 × 1042 kilograms. That's a 3 followed by 42 zeros. If you tried to write out that number, putting 1 zero per second on paper, it would take you 42 seconds just to write the zeros. The number itself represents an amount of mass so vast that describing it in familiar terms becomes impossible. All of Earth's mass, every atom in our planet from the iron core to the upper atmosphere, totals about 6 to 6x 10 to 7 24 kilograms. Andromeda contains 500 million trillion times more mass than our entire planet. 500 million trillion Earths wouldn't equal Andromeda's mass. But most of that mass isn't even in stars. It's dark matter, that mysterious substance that doesn't interact with light, that we can't see or touch or directly detect, but that we know exists because of its gravitational effects. Dark matter makes up approximately 90% of Andromeda's total mass. All those trillion stars, all those planets, all the gas and dust and black holes, everything that actually emits or reflects light, represents only about 10% of what's actually there. The rest is invisible. We can map its presence by observing how visible matter moves through Andromeda, how stars orbit the galactic center, how the galaxy rotates. Those movements reveal the gravitational pull of something we can't see, something massive, something that outweighs all the visible matter by a factor of 9 to 1. Dark matter forms a massive halo around Andromeda, extending far beyond the visible disk, shaping the galaxy's structure, holding it together, preventing it from flying apart as it rotates. The structure of Andromeda itself is a masterpiece of cosmic architecture. Like our own Milky Way, Andromeda is a spiral galaxy. But whereas the Milky Way has a relatively simple four-armed spiral structure, Andromeda is more complex, more elaborate. It has a bright central bulge, a dense concentration of older, yellowish stars packed tightly around the galactic core. This bulge contains some of the oldest stars in the galaxy, ancient suns that formed billions of years ago when Andromeda was young. Surrounding that bulge is a disk, the main body of the galaxy, extending outward in a vast flat plane. And within that disk, spiral arms wind outward from the centre like the arms of a cosmic hurricane frozen in time. These arms aren't solid structures, they're density waves, regions where stars and gas are compressed together more tightly, making them appear brighter. Stars drift in and out of these arms as they orbit the galactic centre, spending some time in the dense arm regions and other times in the less dense inter-arm spaces. The spiral pattern you see when you look at Andromeda in photographs isn't a permanent structure. It's a traffic jam of stars and gas, constantly shifting and reforming as the galaxy rotates. That rotation itself is remarkable. Andromeda spins. The entire galaxy, all trillion stars and their associated planets and gas clouds, rotates around the galactic center. Stars in the inner regions orbit faster than those farther out, but even stars at the outer edge are moving at hundreds of kilometers per second. Our own Sun, in the Milky Way, orbits our galactic center at about 230 kilometers per second. It takes roughly 225 to 250 million years to complete one full orbit. That means that since the Sun formed 4.6 billion years ago, it has completed only about 20 full trips around the Milky Way. 20 laps in 4.6 billion years. Andromeda's stars follow similar orbital patterns, each one tracing its own path through the galaxy, influenced by the gravitational pull of all the matter around it, both visible and dark. The galaxy as a whole doesn't rotate like a solid disk. It rotates differentially, with different regions moving at different speeds, creating the spiral structure as faster-moving inner regions compress gas and dust into those distinctive arms. At the centre of Andromeda, like at the centre of most large galaxies, lurks a supermassive black hole. This isn't some stellar mass black hole formed from a collapsed star. This is a monster, a gravitational beast weighing in at approximately 100 to 200 million solar masses. For comparison, the supermassive black hole at the centre of our galaxy, Sagittarius AM, masses about 4 million solar masses. Andromeda's central black hole is 25 to 50 times more massive. It sits at the exact centre of the galaxy, anchoring the entire structure, its immense gravity influencing the orbits of millions of stars around it. Stars in the innermost regions orbit this black hole at tremendous speeds, whipping around in tight orbits that take just years or decades to complete. And like most supermassive black holes, it's not currently very active. It's not consuming massive amounts of material, not generating brilliant jets of radiation, not blazing with the light of an active galactic nucleus. It's relatively quiet, occasionally consuming a wayward star or gas cloud that ventures too close, but mostly just sitting there, a gravitational anchor around which everything else orbits. But Andromeda isn't alone out there in the darkness. It doesn't drift through intergalactic space in isolation. Like the Milky Way, Andromeda is accompanied by satellite galaxies, smaller galaxies caught in its gravitational grip, orbiting around it like moons around a planet. We've identified at least 14 confirmed satellite galaxies around Andromeda, though there are likely more waiting to be discovered. These satellites range in size from dwarf spheroidal galaxies containing just a few million stars to larger dwarf elliptical galaxies with billions of stars. They orbit Andromeda at various distances, some relatively close, others farther out in the dark matter halo. The two largest and most prominent are M32 and M110, both visible in telescopic images of Andromeda. M32 is a compact elliptical galaxy, dense and bright, containing perhaps a few billion stars compressed into a relatively small volume. M110 is larger but more diffuse, a dwarf elliptical spreading its stars across a wider area. Both are gravitationally bound to Andromeda, forever trapped in orbit around the larger galaxy, their fates tied to whatever future awaits their massive companion. These satellite galaxies aren't permanent structures though. Over time, tidal forces from Andromeda's gravity will tear them apart. Stars will be stripped away from the satellites and absorbed into Andromeda's outer halo. We can see this process happening in real time with some of Andromeda's satellites. Stellar streams, long ribbons of stars stretching across space, mark the death throes of satellite galaxies being ripped apart by tidal forces. These streams are the remnants of smaller galaxies that got too close, that ventured into regions where Andromeda's gravity became too strong to resist. Their stars are being pulled away, stretched into long filaments that will eventually merge completely with Andromeda's halo. It's galactic cannibalism, Andromeda consuming its smaller neighbours, growing larger by incorporating their stars into its own structure. And this process has been happening throughout Andromeda's history. The galaxy has likely consumed dozens of smaller galaxies over billions of years, each one adding its stars to Andromeda's total mass, each one leaving behind faint traces in the form of stellar streams and disrupted star clusters. The Milky Way does the same thing, by the way. Our galaxy has its own collection of satellite galaxies, including the famous Magellanic Clouds visible from Earth's southern hemisphere, and we're currently in the process of consuming some of them. The Sagittarius dwarf elliptical galaxy is being torn apart right now, its stars streaming into the Milky Way's halo. Over the next few billion years, it will cease to exist as a distinct structure, its stars completely absorbed into our galaxy. This is how large galaxies grow, not through some internal process of star formation alone, but through mergers and cannibalization of smaller galaxies. It's survival of the biggest in cosmic terms. Large galaxies attract smaller ones, pull them in, tear them apart, and incorporate their stars. The history of Andromeda, like the history of the Milky Way, is a history of countless mergers and collisions, each one adding to the galaxy's mass and complexity. Now let's talk about what's inside Andromeda beyond just stars, because galaxies aren't just collections of suns scattered randomly through space. They're complex ecosystems containing multiple types of objects and structures, each playing a role in the galaxy's evolution. Start with star clusters. Andromeda contains hundreds of globular clusters, dense spherical collections of stars bound together by gravity. Each globular cluster can contain anywhere from tens of thousands to millions of stars packed into a relatively small volume, maybe 100 to 200 light-years across. These clusters orbit Andromeda's galactic centre, typically found in the halo rather than the disk. Many of them are incredibly old, dating back nearly to the galaxy's formation. Their stars are ancient, often more than 10 billion years old, making them some of the oldest objects in the galaxy. Studying these globular clusters gives us insights into Andromeda's early history, into the conditions that existed when the galaxy first formed. Then there are open clusters, looser associations of stars found primarily in the galactic disk, especially in the spiral arms. Unlike globular clusters with their millions of tightly packed ancient stars, open clusters contain dozens to hundreds of younger stars, often still associated with the nebula from which they formed. These clusters are stellar nurseries, regions where stars are actively being born from collapsing clouds of gas and dust. The stars in open clusters are gravitationally bound to each other, but only loosely. Over time, typically over millions or billions of years, the cluster will disperse as its member stars drift apart, each going its own way through the galaxy. But for a while, they travel together, born from the same cloud, sharing a common origin. Speaking of stellar nurseries, Andromeda is still actively forming new stars. Despite being an ancient galaxy, billions of years old, star formation continues within its spiral arms. Giant molecular clouds, vast regions of cold gas and dust, collapse under their own gravity to form new stars. These clouds can be enormous, containing enough material to create thousands or even millions of stars. When conditions are right, when the cloud becomes dense enough and cool enough, gravity takes over and the cloud fragments into smaller clumps. Each clump collapses further, heating up as gravitational potential energy converts to thermal energy. Eventually, at the core of each collapsing clump, temperatures and pressures become high enough to ignite nuclear fusion. Hydrogen begins fusing into helium. A star is born, and this process is happening right now, at this very moment, in multiple locations throughout Andromeda. New stars are igniting. New planetary systems are forming. New worlds are coalescing from disks of gas and dust around young stars. But star formation in Andromeda isn't as vigorous as it once was. Like many large spiral galaxies, Andromeda has passed through its most active star-forming phase. Billions of years ago, when the galaxy was younger and contained more pristine gas, star formation rates were much higher. But over time, as gas was consumed and turned into stars, as successive generations of stars lived and died and returned some of their material to space, the rate of new star formation decreased. Today, Andromeda forms new stars at a rate of roughly 1 solar mass per year. That might sound like a lot, but it's actually quite modest for a galaxy of Andromeda's size. The Milky Way forms new stars at a similar rate, maybe slightly less. For comparison, during the peak of star formation in the early universe, some galaxies were forming hundreds or even thousands of solar masses worth of new stars every year. Andromeda's star-forming days aren't over, but they've definitely slowed down compared to its youth, and alongside all this ongoing stellar activity, stars are also dying throughout the galaxy. Massive stars, those with many times the Sun's mass, burn through their fuel quickly. They live fast and die young, sometimes in just a few million years. When they exhaust their nuclear fuel, they can no longer support themselves against gravity. The core collapses catastrophically, and the star explodes in a supernova, one of the most energetic events in the universe. For a brief period, a single supernova can outshine the entire galaxy. It releases as much energy in a few weeks as our Sun will emit over its entire 10 billion year lifetime. These explosions are visible across intergalactic distances. Astronomers have observed supernovae in Andromeda, sudden bright points of light appearing where no star was visible before, shining brilliantly for weeks or months before fading away. Each supernova seeds the galaxy with heavy elements, scattering iron and gold and carbon and oxygen into the interstellar medium. These elements, forged in the cores of massive stars and dispersed by their deaths, will eventually be incorporated into new generations of stars and planets. Smaller stars like our Sun die more quietly. They swell into red giants, shed their outer layers into beautiful planetary nebulae, and leave behind dense white dwarf cores. These white dwarfs will cool slowly over trillions of years, eventually becoming cold, dark cinders floating through space. But that process takes longer than the current age of the universe. Every white dwarf in existence today is still hot, still radiating away its residual heat. Andromeda contains billions of these stellar remnants, the corpses of sun-like stars that exhausted their fuel long ago. They're difficult to see individually because they're so small and dim, but collectively they represent a significant fraction of the galaxy's stellar population. And then there are neutron stars and black holes, the remnants of the most massive stars. When a star much more massive than the Sun goes supernova, its core can collapse into an object so dense that electrons and protons merge into neutrons. The result is a neutron star, an object containing more mass than the Sun compressed into a sphere just 20 kilometers across. Neutron stars are among the densest objects in the universe. A teaspoon of neutron star material would weigh about 1 billion tons on Earth. These objects spin rapidly, often many times per second, and possess magnetic fields billions of times stronger than anything we can create in laboratories. Some neutron stars emit beams of radiation from their magnetic poles. As they spin, these beams sweep across space like lighthouse beams. If one of these beams happens to point toward Earth, we detect regular pulses of radiation. We call these objects pulsars. Andromeda surely contains thousands or even millions of neutron stars, most of them invisible to us, silently spinning in the darkness between stars. And if the collapsing stellar core is massive enough, not even neutron degeneracy pressure can stop the collapse. The core continues shrinking until it becomes a black hole, a region of space-time where gravity is so strong that not even light can escape. These stellar mass black holes formed from individual collapsing stars typically range from a few to a few dozen solar masses. They're completely invisible unless they're actively consuming matter. If a black hole has a companion star, it can pull material from that star. The infalling matter forms an accretion disk around the black hole, spiraling inward, heating up due to friction, and emitting X-rays before finally crossing the event horizon. We can detect these X-ray binaries and infer the presence of black holes from the behaviour of their companion stars. Andromeda contains many such systems, stellar mass black holes scattered throughout the galaxy, most of them isolated and invisible, but some actively feeding on companion stars and revealing their presence through high-energy radiation. Between all these objects, between the stars and star clusters and black holes and neutron stars, exists the interstellar medium. This isn't empty space. It's a thin gas composed primarily of hydrogen and helium, with trace amounts of heavier elements. The density is incredibly low, typically just 1 atom per cubic centimetre, far lower than even the best vacuum we can create in laboratories. But across the vast distances of galactic space, all that thin gas adds up to significant mass. The interstellar medium makes up about 10% of the visible matter in Andromeda. It exists in various states. Some regions are cold and dense, the molecular clouds where stars form. Other regions are warm and diffuse, heated by radiation from nearby stars. Still other regions are extremely hot, heated to millions of degrees by supernova shockwaves or stellar winds. This hot gas emits X-rays, invisible to our eyes but detectable by space-based X-ray telescopes. And mixed throughout the interstellar medium is dust. Not dust like you find on furniture, but tiny solid particles, mostly carbon and silicates, each grain smaller than a wavelength of light. These dust grains form in the atmospheres of cool stars and in the ejecta from supernovae. They're scattered throughout the galaxy, particularly concentrated in the spiral arms where star formation occurs. Dust might seem insignificant, but it plays crucial roles in galactic ecology. It absorbs and scatters light, creating the dark lanes visible in photographs of spiral galaxies. It serves as a surface on which molecules can form, enabling chemistry that wouldn't occur in pure gas. And it provides the seeds from which planets eventually coalesce. Every solid object in the universe, every planet and asteroid and grain of sand, ultimately traces its origin to interstellar dust. Now let's put Andromeda in context by comparing it directly to our home galaxy, the Milky Way. Because understanding Andromeda's true scale requires measuring it against something familiar, something we can relate to from our position inside our own galaxy. And the comparison is humbling. In almost every measurable way, Andromeda is larger, more massive, more luminous than the Milky Way. Not by a small margin either, by factors that make our galaxy seem almost like Andromeda's smaller sibling. Start with the most basic measurement: diameter. The Milky Way stretches approximately 100,000 light-years across, depending on exactly where you define its edge. That's already an incomprehensible distance. Light leaving one edge of our galaxy takes 100,000 years to reach the opposite edge. During that time, entire civilizations could rise and fall. Species could evolve and go extinct. Ice ages could come and go. Continents could drift thousands of kilometers. And throughout all that change, that light just travels, crossing the void between stars at the maximum possible speed. But Andromeda is 220,000 light-years across, more than twice the diameter. If you could somehow place both galaxies side by side and look at them from a distance, Andromeda would dominate the view. It would stretch more than twice as far in every direction, and because volume scales with the cube of diameter, Andromeda's greater size translates into vastly more space. Remember, it has roughly 10 times the volume of the Milky Way, 10 times more territory, 10 times more room for stars and planets, and all the phenomena that occur in galaxies. That size difference becomes even more apparent when you look at stellar populations. The Milky Way contains somewhere between 200 and 400 billion stars. The exact number is uncertain because we can't directly observe large portions of our own galaxy. We're inside it, embedded in the galactic disk, and vast regions are obscured by dust and intervening stars. But best estimates put our stellar population in that range. Hundreds of billions of stars. It seems like an enormous number, and it is. But Andromeda contains approximately 1 trillion stars. That's at least twice as many as the Milky Way, possibly 3 times as many. 1 trillion individual suns, each one a nuclear furnace, each one potentially hosting planets. Mass tells a similar story. The Milky Way's total mass, including both visible matter and dark matter, is estimated at roughly 1 to 1.5 trillion solar masses. Andromeda clocks in at approximately 1.5 trillion solar masses, possibly more. Some estimates push Andromeda's mass even higher, to 2 trillion solar masses or beyond. The exact figure is uncertain because measuring galactic masses, especially the dark matter component, is challenging. But by any measure, Andromeda equals or exceeds the Milky Way's mass. When you account for all the matter, visible and invisible, Andromeda is at least as massive as our galaxy, likely more so, and that mass difference has consequences. More mass means stronger gravity. Stronger gravity means a deeper gravitational well. A deeper well means satellites and companion galaxies are more tightly bound, held more securely in orbit. Andromeda's greater mass gives it a stronger gravitational grip on its surroundings. The central supermassive black holes tell the same story of scale. Sagittarius Aos, the black hole at the centre of the Milky Way, weighs in at about 4 million solar masses. It's a monster, no question. Its gravity shapes the orbits of stars in the galactic centre, some of which orbit so closely they complete a full revolution in just years. But Andromeda's central black hole is 25 to 50 times more massive, somewhere between 100 and 200 million solar masses. It's not just bigger, it's in a completely different category. The gravitational influence of such a massive black hole extends much farther, affecting many more stars, shaping the inner structure of the galaxy across a larger volume of space. Why does Andromeda have a more massive central black hole? Probably because it's consumed more material over its lifetime. Supermassive black holes grow by accreting gas and by merging with other black holes during galaxy collisions. Andromeda has likely experienced more mergers, more violent interactions with other galaxies throughout its history. Each merger brought new material to the central regions. Some of that material was consumed by the central black hole, causing it to grow larger. Even the satellite galaxies paint a picture of Andromeda's dominance. The Milky Way has several dozen known satellite galaxies, with the two largest being the Large and Small Magellanic Clouds. These are substantial dwarf galaxies visible from Earth's southern hemisphere. But Andromeda has at least 14 confirmed satellites, and ongoing searches continue to discover more. While the Milky Way's satellite system is impressive, Andromeda's appears more extensive, more massive overall. This makes sense given Andromeda's larger size and mass. A more massive galaxy has stronger gravity, allowing it to capture and hold on to more satellites across a larger volume of space. The entire local group, the collection of galaxies that includes both the Milky Way and Andromeda, along with dozens of smaller galaxies, is essentially dominated by these two giants. And of the two, Andromeda is the larger, the more massive, the more influential gravitationally. But here's something interesting. Despite being larger and more massive, Andromeda isn't forming stars much faster than the Milky Way. Star formation rate in both galaxies is roughly similar, around 1 solar mass per year, give or take. Why? Because star formation depends on available cold gas, not just total mass. Both galaxies have consumed most of their pristine gas over billions of years of star formation. What remains is recycled material, gas returned to the interstellar medium by dying stars, plus small amounts of fresh gas accreted from intergalactic space. Andromeda has more gas in absolute terms, but relative to its size and stellar mass, the proportions are similar to the Milky Way. Both are mature galaxies past their peak star-forming years. They're not dead, not by any means. New stars continue to be born in both galaxies. But the frenzied star formation that characterized their youth has slowed to a steadier, more modest pace. The structural similarities are striking too. Both are spiral galaxies, though Andromeda's spiral structure is somewhat different from the Milky Way's. The Milky Way is classified as a barred spiral, meaning it has a bar-shaped structure of stars extending from the central bulge, with spiral arms emanating from the ends of the bar. Andromeda lacks this prominent bar structure, or if it has one, it's much less developed. Its spiral arms emerge more directly from the central bulge. Both galaxies have prominent disks, flattened structures where most of the stars reside, with spiral arms winding through these disks. Both have central bulges, dense concentrations of older stars around the galactic core. Both are surrounded by extended halos of dark matter, invisible but gravitationally dominant. In fundamental architecture, they're siblings, variations on the same galactic theme, and both galaxies are surrounded by enormous halos of hot gas, extending far beyond their visible structures. This gas is extremely diffuse and extremely hot, heated to millions of degrees. It doesn't emit visible light, but it radiates X-rays detectable by space-based telescopes. These halos contain significant amounts of mass, perhaps as much as all the visible stars combined. Where does this hot gas come from? Partly from stellar winds and supernovae, which heat and eject gas into the galactic halo. Partly from gas falling into the galaxy from intergalactic space, heating up as it falls into the gravitational well. This hot halo plays important roles in galactic ecology. It serves as a reservoir of gas that can cool and fall back into the disk, fueling future star formation. It helps regulate the temperature and pressure of the galaxy's surroundings. And its presence tells us that galaxies aren't isolated systems with sharp boundaries. They're embedded in extended halos of hot gas that blur the line between the galaxy and intergalactic space. Looking at both galaxies from outside, from a vantage point somewhere in intergalactic space, you'd see similarities and differences. Both would appear as magnificent spiral structures, disks of stars with arms winding outward from bright central bulges. Both would glow with the combined light of hundreds of billions or trillions of stars. But Andromeda would appear larger, more luminous, more imposing. Its greater size and stellar population would make it the more prominent of the two. If an alien astronomer somewhere in a distant galaxy happened to observe our local group, they might catalogue both the Milky Way and Andromeda. But Andromeda would likely be the one that caught their attention first, the dominant galaxy of the pair, with the Milky Way noted as its companion, its smaller sibling. This comparison isn't meant to diminish the Milky Way. Our galaxy is magnificent in its own right. A vast cosmic city containing hundreds of billions of stars and everything that comes with them, is our home on the largest scale we can conceptualize. Every human who has ever lived, every story ever told, every war ever fought, every discovery ever made, all of it happened here, in this one galaxy, on one planet orbiting one star among hundreds of billions. The Milky Way contains multitudes, but Andromeda contains more. It's simply larger, more massive, more extensive in almost every measurable way. And recognizing that helps us understand our place in the cosmic hierarchy. We're not in the largest galaxy in the universe, not even close. We're not in the largest galaxy in our galactic group. We're in the second largest, the runner-up, the junior partner in a binary system dominated by our larger neighbour. And that neighbour is getting closer. This is the fact that transforms Andromeda from an interesting astronomical object into something more immediate, more consequential. Andromeda isn't just sitting there in space at a fixed distance, it's moving. Specifically, it's moving toward us. The space between our galaxies is shrinking, and it has been shrinking for a very long time. When astronomers first measured Andromeda's velocity using spectroscopy, they discovered something remarkable. Unlike most galaxies in the universe, which are receding from us due to cosmic expansion, Andromeda is approaching. Its light shows a blue shift, meaning the wavelengths are compressed, shortened, which happens when an object moves toward you. The degree of blue shift tells us how fast Andromeda is approaching, and the answer is approximately 110 kilometers per second. That's about 400,000 kilometers per hour. For comparison, Earth orbits the Sun at about 30 kilometers per second. Andromeda is approaching us more than 3 times faster than Earth moves through space around the Sun. Why is Andromeda approaching when most galaxies are receding? Because gravity, at local scales, overpowers cosmic expansion. On the larger scales, across billions of light years, the expansion of space dominates. Distant galaxies recede from us, carried away by the expansion of space itself, but locally, within relatively nearby regions of the universe, gravity can overcome that expansion. The Milky Way and Andromeda are close enough, massive enough, that their mutual gravitational attraction exceeds the expansion of space between them. They're pulling on each other, and they have been for billions of years. That pull has been slowly accelerating both galaxies toward each other. The distance between them has been decreasing for eons, and it will continue decreasing until finally, inevitably, the two galaxies collide. The collision between the Milky Way and Andromeda isn't speculation. It's not a possibility or a hypothesis. It's an inevitability, a cosmic event already in motion, already unavoidable. The mathematics are clear, the trajectories are set. Barring some completely unforeseen intervention, something that would require physics we don't understand, these two galaxies will merge. The only questions are exactly when and exactly how. Current models, based on precise measurements of Andromeda's position and velocity, predict the first close encounter will occur in approximately 4.5 billion years. That might seem like an incomprehensibly distant future, and it is. For context, 4.5 billion years ago, Earth was just forming from the protoplanetary disk around the young Sun. No life existed yet. The planet was a ball of molten rock being bombarded by asteroids and comets. Everything that has happened since then, the entire history of life on Earth from the first simple cells to the present day, represents the same amount of time that remains before Andromeda arrives. But here's the thing about cosmic timescales. They're deceptive. 4.5 billion years feels like forever from a human perspective. Civilizations rise and fall in centuries. Species evolve and go extinct over millions of years. Even on geological timescales, 4.5 billion years represents the entire history of the Earth. But in cosmic terms, in the lifetime of galaxies and stars, 4.5 billion years is not that long. It's a significant fraction of the current age of the universe, which is 13.8 billion years. But for galaxies, which can exist for trillions of years in principle, 4.5 billion years is almost immediate. It's soon. Right around the corner, cosmically speaking, and we can already see it coming. We can measure Andromeda's approach. We can track its motion across the sky. The collision might be billions of years away, but it's not distant in the sense of being uncertain or theoretical. It's as real and inevitable as tomorrow's sunrise, just separated from us by a vastly longer span of time. What will happen when these two galaxies collide? The word collision might conjure images of destruction, of objects smashing together, shattering into fragments. But galactic collisions aren't like that. They're not violent in the way you might imagine. Here's why. Galaxies are mostly empty space. Yes, they contain hundreds of billions or trillions of stars, but those stars are separated by vast distances. The distance between stars is enormous compared to the size of the stars themselves. Our Sun is about 1.4 million kilometers in diameter. The nearest star, Proxima Centauri, is 4.24 light-years away, which equals about 40 trillion kilometers. The space between stars is roughly 30 million times larger than the stars themselves. If you shrunk the Sun down to the size of a grain of sand, about 1 millimeter across, the nearest star would be another grain of sand about 30 kilometers away. That's how much empty space exists between stars. So when two galaxies collide, when their stars pass through each other, actual stellar collisions are extraordinarily rare, almost non-existent. Stars will pass by each other, sometimes coming relatively close by cosmic standards, but actual impacts, actual collisions between stars, will be vanishingly unlikely. The probability of our Sun colliding with a star from Andromeda during the merger is effectively zero. You could run the collision simulation 1,000,000 times, with slightly different initial conditions each time, and in almost none of them would our Sun hit another star. The distances are just too large. The galaxies are too empty. Stars will sail past each other like two swarms of gnats passing through each other, each swarm containing trillions of individuals, but so much space between them that actual impact never occur. But don't mistake the rarity of stellar collisions for a lack of drama. Because even though stars won't hit each other, the gravitational interactions between two entire galaxies' worth of stars will be catastrophic for galactic structure. Imagine you're a star in the Milky Way's disk, orbiting the galactic centre in a nice stable orbit that you've followed for billions of years. You're moving at several hundred kilometers per second, as are all the other stars around you, all of you orbiting together in the same general direction, all contributing to the galaxy's overall rotation. Then Andromeda arrives. Suddenly there's a second galaxy worth of stars, a second enormous gravitational mass approaching at high speed. That mass doesn't just sit there, it pulls on you. It pulls on every star in the Milky Way, and the pull isn't uniform. Stars on the side of the Milky Way closer to Andromeda feel a stronger pull than stars on the far side. This differential pull, this tidal force, begins to distort the Milky Way structure. As Andromeda gets closer, these tidal forces intensify. The Milky Way's disk, that nice flat structure that has existed for billions of years, starts to warp. Stars near the interaction zone, near where the two galaxies come closest, experience gravitational tugs from two different galactic centers. Their orbits become chaotic. Some stars are accelerated, flung outward at high speeds. Others are decelerated, falling inward toward one galactic center or the other. the orderly rotation of the disk breaks down into chaos. And this happens on both sides. Andromeda is also being torn apart by the Milky Way's gravity. Tidal forces work both ways. We're pulling on Andromeda just as hard as it's pulling on us. Both galaxies will be distorted, stretched, their structures disrupted by the mutual gravitational interaction. The first pass will be dramatic but not final. Computer simulations of galactic mergers show that when two large spiral galaxies collide, they rarely merge on the first encounter. Instead, they interpenetrate, passing through or past each other, each galaxy emerging from the interaction heavily distorted but still recognizable as a separate structure. But here's what happens next. Both galaxies have lost orbital energy to the gravitational interaction. They're moving slower than they were before, and they're still gravitationally bound to each other. So after passing through each other, after moving apart for a while, they'll slow down, stop, and fall back together for a second encounter. This second pass will be even more destructive than the first, because the galaxies will be moving slower, spending more time in close proximity, giving tidal forces more time to work. More stars will be ejected, more structure will be disrupted. The spiral arms, those beautiful defining features of both galaxies, will be shredded and scattered. After the second pass, the same thing happens again. The galaxies separate, but not as far as before. They slow, stop, fall back together for a third encounter. Each pass brings them closer. Each interaction dissipates more orbital energy. After several passes, maybe 3 or 4 or 5, the two galactic cores will finally merge, settling into the center of a new combined structure. The timescale for this entire process, from first encounter to final merger, is long even by cosmic standards, probably about 2 billion years. So if the first close approach happens in 4.5 billion years, the final merger, the point where the two galaxies have completely combined into a single structure, won't occur until roughly 6.5 billion years from now. That's nearly half the current age of the universe from now. But again, in cosmic terms, it's not that far. It's eventual, certain, already in motion. And what will the final merged galaxy look like? It won't be a spiral galaxy. The beautiful spiral structures of both the Milky Way and Andromeda will be destroyed during the merger. The orderly rotation required to maintain spiral arms will be disrupted beyond recovery. Too many stars will have been thrown into chaotic orbits. Too much angular momentum will have been distributed in random directions. Instead, the merged galaxy will most likely be an elliptical galaxy, a roughly spherical or ellipsoidal blob of stars with no disk, no spiral arms, no organized rotation, just a vast swarm of stars moving in random directions, held together by their mutual gravity, orbiting the combined mass of both original galactic centers. Astronomers have already given this future merged galaxy a name, Milkomeda, or sometimes Milkdromeda, a portmanteau combining Milky Way and Andromeda, acknowledging that this future galaxy will be the offspring of both parents, containing stars and matter from both progenitors, but recognizable as neither. Milkomeda will be enormous. It will contain roughly 1.2 to 1.5 trillion stars, the combined stellar populations of both galaxies minus whatever stars get ejected during the merger, and stars will be ejected, lots of them. Computer simulations suggest that during violent galaxy mergers, a significant fraction of stars can be flung out of the system entirely, ejected at high enough velocities that they escape the combined gravitational pull of the merged galaxy. These stars become intergalactic wanderers, lonely suns drifting through the void between galaxies, orphaned from their home, doomed to spend the rest of their lives in the darkness of intergalactic space. Estimates vary, but perhaps 10 to 20% of stars from both galaxies might suffer this fate. That means hundreds of billions of stars ejected, cast out into the void, along with whatever planets orbit them. Our solar system could be one of them. The Sun, along with Earth and the other planets, might be ejected during the merger. Computer simulations can't predict the fate of any individual star. The interactions are too complex, too chaotic, too dependent on the exact initial conditions. But statistically, there's a non-trivial chance that our solar system gets flung out of the merged galaxy entirely. Imagine that. Earth, 4 billion years older than today, still orbiting the Sun, but now the Sun is no longer part of any galaxy. The night sky, instead of being filled with the glow of the Milky Way's billions of stars, would be almost completely dark. A few nearby ejected stars might be visible, fellow exiles from the merger. But the galaxies themselves, Milkomeda and any other nearby galaxies, would appear as distant smudges of light, separated from Earth by millions of light-years of empty intergalactic space. It would be the loneliest night sky imaginable, quiet, dark, isolated. But ejection, while possible, isn't the most likely outcome for our solar system. More probably, we'll remain part of the merged galaxy. The Sun will end up in some random orbit within Milkomeda, possibly in the inner regions, possibly in the outer halo, possibly somewhere in between. The orbit will be nothing like our current orbit in the Milky Way. It will be more chaotic, less circular, taking us on a long elliptical path through the merged galaxy. At times we might plunge through the dense central regions where stellar density is high. At other times we might drift out into the sparse outer reaches where stars are few and far between. The predictable, stable galactic environment we've enjoyed for billions of years will be replaced by something more variable, more dynamic. What about the Sun itself? What about Earth? Will they survive the merger? Almost certainly yes, at least initially. Remember, stellar collisions are vanishingly rare. The Sun won't hit another star. Earth won't be destroyed by some direct catastrophic impact, but there are other concerns. If our orbit happens to take us through dense regions of Milkomeda, close encounters with other stars become more likely. A star passing within a light year or so of the Sun could gravitationally perturb the orbits of planets, potentially destabilizing the solar system. More significantly, a close stellar encounter could disrupt the Oort cloud, that distant shell of comets surrounding the solar system. Gravitational perturbations could send swarms of comets falling inward toward the Sun. Some might collide with Earth. A major cometary bombardment could cause mass extinctions, dramatically altering or even ending whatever life exists on Earth at that time. But here's a more fundamental problem. By the time the merger completes, about 6.5 billion years from now, Earth will likely already be uninhabitable. The Sun is slowly getting brighter as it ages. This happens to all stars like the Sun. As hydrogen fuses into helium in the core contracts slightly and heats up, causing the fusion rate to increase, which makes the star more luminous. The Sun's luminosity has increased by about 30% since it first formed 4.6 billion years ago. And it will continue increasing. In about 1 billion years, maybe less, the Sun will be bright enough that Earth's oceans will begin to evaporate. Water vapour is a greenhouse gas. More water vapour in the atmosphere means more warming, which causes more evaporation, which causes more warming, a runaway feedback loop. Eventually, Earth will experience a runaway greenhouse effect similar to what happened on Venus. Surface temperatures will soar to hundreds of degrees. The oceans will boil away completely. Any complex life still on the planet will die. Earth will become a hot, dead, sterile rock orbiting an increasingly luminous star. This will happen long before Andromeda arrives. By the time the galaxies merge, Earth will have been uninhabitable for billions of years. Whatever happens during the merger, whatever gravitational chaos ensues, Earth will already be dead. If humanity still exists in some form, if our descendants or our creations have survived across those incomprehensible spans of time, they won't be on Earth watching the merger. They'll be somewhere else, maybe on planets around other stars scattered throughout the galaxy or galaxies, maybe in artificial habitats, space-based structures designed to last for geological timescales, maybe in forms we can't even imagine, post-biological entities that have transcended the limitations of organic life. Or maybe they'll be gone, extinct, joined by countless other species in the long history of life and death in the universe. But the merger's impact extends beyond just the two galaxies directly involved. The entire local group, that collection of dozens of galaxies gravitationally bound together, will be affected. The local group is essentially dominated by two massive members, the Milky Way and Andromeda. Everything else, all the dwarf galaxies and satellite galaxies and irregular galaxies, are small by comparison. Most of them are gravitationally bound to either the Milky Way or Andromeda, orbiting one or the other like moons around planets. When the two central masses collide and merge, those satellite galaxies will experience gravitational chaos. Their orbits will be disrupted. Some will be pulled into the merger itself, consumed by the growing Milkomeda. Others might be ejected, flung out of the local group entirely by gravitational slingshot effects. A few might survive in new orbits around the merged galaxy, but their environments will be transformed, their futures uncertain. The Magellanic Clouds, those two prominent satellite galaxies of the Milky Way visible from Earth's southern hemisphere, face particularly uncertain fates. They're already in somewhat precarious orbits around the Milky Way. The large Magellanic Cloud contains maybe 30 billion stars. The small Magellanic Cloud has perhaps 3 billion. Both are being gradually torn apart by the Milky Way's tidal forces. Streams of stars and gas stripped from the Magellanic Clouds stretch across the southern sky, though they're too faint to see with the naked eye. When Andromeda arrives and the merger begins, the gravitational chaos will intensify dramatically. The Magellanic Clouds might be pulled into the merger zone, their stars scattered and absorbed into Milkomeda, or they might be ejected, flung out into intergalactic space to become isolated dwarf galaxies, no longer bound to any large galaxy, drifting alone through the void. Triangulum, the third largest galaxy in the local group after Andromeda and the Milky Way, also faces an uncertain future. Triangulum is a spiral galaxy containing perhaps 40 billion stars, located about 2.7 million light-years from the Milky Way. It's currently in the gravitational sphere of influence of Andromeda, possibly even in orbit around Andromeda, though the exact nature of their relationship is unclear. When Andromeda collides with the Milky Way, Triangulum will either be drawn into the merger, adding its stars to the growing pile, or it will be disrupted and scattered, its structure torn apart by gravitational forces from two merging giant galaxies. Computer simulations offer various possible outcomes, depending on Triangulum's exact velocity and trajectory, which we haven't measured with perfect precision. But one thing is certain: Triangulum won't emerge from the merger unchanged. Its fate is tied to the collision, whether it joins Milkomeda or is destroyed in the process. And consider what all this means for star formation. Galaxy mergers, despite being destructive to galactic structure, often trigger intense bursts of star formation. Here's why. Both the Milky Way and Andromeda contain vast reservoirs of cold gas, primarily hydrogen, spread throughout their disks. Under normal conditions, this gas forms stars at a relatively modest rate, one solar mass per year or so in each galaxy. But during a merger, gravitational forces compress this gas. Tidal interactions create shock waves that propagate through the interstellar medium. Gas clouds that were stable for billions of years suddenly become unstable, collapsing under their own gravity. The result is a starburst, a period of dramatically increased star formation lasting perhaps a few 100 million years. During this starburst phase, Milkomeda might form new stars at a rate hundreds of times higher than either progenitor galaxy. Thousands of solar masses worth of new stars per year, maybe more. This starburst will consume much of the available gas in both galaxies. The Milky Way and Andromeda each contain billions of solar masses worth of gas available for star formation. When compressed and disrupted by the merger, much of this gas will rapidly convert into stars. Giant molecular clouds will collapse en masse. Stellar nurseries will ignite across vast regions of the merging system. New star clusters, some containing millions of stars, will form in the merger's most active regions. The combined light from all these newly forming stars will make Milky incredibly luminous for a brief period, at least by cosmic standards. It will outshine either of its progenitor galaxies by a significant factor. If an astronomer in some distant galaxy happened to be observing our local group during this period, they would see a dramatic brightening as the merger progresses and the starburst ignites. But starbursts are short-lived phenomena. After a few 100 million years, the available gas will be exhausted. Either it will have been consumed in star formation, or it will have been heated and blown out of the galaxy by stellar winds and supernovae. Once the starburst ends, once the gas is gone, star formation in Milky will essentially cease. The galaxy will become what astronomers call red and dead, an elliptical galaxy composed almost entirely of old stars with little to no ongoing star formation. New stars will no longer be born. The stellar population will age gradually over billions of years, with massive short-lived stars dying off first, leaving behind progressively more long-lived, smaller stars. Eventually, many billions of years after the merger completes, Milky will be dominated by small red dwarf stars and stellar remnants, white dwarfs, neutron stars and black holes. It will be a galaxy in its twilight years, slowly fading as its stars exhaust their fuel and die, with no new generations of stars being born to replace them. The central regions of Milky will host a truly monstrous supermassive black hole. When the two galactic cores finally merge, when the Milky Way's central black hole and Andromeda's central black hole spiral together and coalesce, the resulting black hole will be enormous. Remember, the Milky Way's black hole weighs about 4 million solar masses. Andromeda's weighs between 100 and 200 million solar masses. When they merge, conservation of mass means the resulting black hole will weigh approximately 104 to 204 million solar masses, essentially the sum of the two progenitors. This merged black hole will be one of the largest in the local universe, a gravitational beast anchoring the centre of Milky, influencing the orbits of millions of stars around it. The merger of two supermassive black holes is one of the most energetic events possible in the universe, exceeded only by the Big Bang itself. As the black holes spiral inward toward each other, they will emit gravitational waves, ripples in space-time predicted by Einstein's general relativity. These waves will carry away orbital energy, causing the black holes to spiral closer together, faster and faster. The frequency and amplitude of the gravitational waves will increase as the black holes approach, reaching a crescendo in the final moments before merger. When they finally collide, coalescing into a single black hole, they will release a tremendous burst of gravitational radiation. This event will be detectable by gravitational wave observatories across the universe, assuming such observatories still exist billions of years in the future. The gravitational waves from the merger of Milky central black holes will propagate outward at the speed of light, carrying information about the event to any civilization advanced enough to detect them. But here's something to consider. If our solar system survives the merger, if Earth somehow remains in the habitable zone around the Sun despite the Sun's increasing luminosity, if complex life still exists on our planet billions of years from now, and if that life includes beings capable of understanding what's happening, what would they see in the sky? During the early phases of the merger, when Andromeda first approaches, it would dominate the night sky. Instead of appearing as a faint smudge barely visible to the naked eye, Andromeda would grow larger and brighter over millions of years. At first, the changes would be imperceptible across human lifetimes, but across geological timescales, the transformation would be dramatic. Andromeda would swell in apparent size, eventually appearing larger than the full moon, then larger still. Its spiral structure would become clearly visible to the naked eye, a vast cosmic whirlpool filling a significant portion of the sky. As the first close approach neared, Andromeda would fill much of the visible sky. You'd see individual bright regions, giant star-forming nebulae and star clusters visible as distinct features within the larger spiral structure. The combined light from 1 trillion stars would be bright enough to cast shadows at night. The sky would never truly be dark. Even without the moon, even without city lights or any artificial illumination, the night would have a faint glow from Andromeda's light. And as the galaxies interpenetrated during that first pass, the view would become surreal. Stars from Andromeda would be scattered across the sky, mixing with stars from the Milky Way. The familiar constellations, those patterns that have remained essentially unchanged for all of human history, would be transformed beyond recognition. New stars would appear, bright stars from Andromeda, some of them giant stars far more luminous than anything currently visible, would dominate the night sky. The orderly structure of the Milky Way's disk, the band of light arcing across the sky that we call the Milky Way, would be disrupted and fragmented. Between close approaches, as the galaxies separated again before falling back together, the sky would remain chaotic. Tidal tails, long streams of stars pulled out of both galaxies by gravitational forces, would stretch across vast regions of sky. These tails would appear as diffuse glowing arcs, rivers of stars flowing through space. Some stars in these tails might be moving at high velocities relative to the local stellar population, appearing to drift visibly across the sky over thousands or tens of thousands of years. During the starburst phase, when star formation ignites throughout the merging system, brilliant new star clusters would appear. Some regions of sky might host dozens of bright blue stars, massive young stars born in the merger, each one shining with the luminosity of thousands of suns. These stars would live fast and die young, exploding as supernovae after just a few million years, creating spectacular light shows visible even during the day. And finally, after the multiple passes, after the gradual merger of the galactic cores, the night sky would settle into something completely unlike what we see today. Instead of the disk of the Milky Way stretching across the sky, there would be a more uniform glow. Milkomeda, being an elliptical galaxy, doesn't have a prominent disk. Stars would be distributed more spherically, more evenly in all directions. From a planet within Milkomeda, the night sky would show stars in every direction, but without the concentration along one particular band that characterizes our current view of the Milky Way. And depending on where in Milkomeda our solar system ended up, the density of visible stars could vary dramatically. If we ended up in the inner regions near the galactic center, the sky would be crowded with stars, far more than we see today. Thousands or tens of thousands of stars visible to the naked eye, compared to the few thousand visible from Earth today. The night would never be truly dark. If we ended up in the outer halo, the opposite would be true. The sky would be sparse, with fewer visible stars than we see now, and Milkomeda's core would appear as a distant glow, a concentrated smudge of light in one particular direction. But let's step back and consider what this merger means in the broader context of cosmic evolution. Galaxy mergers aren't rare. They're not unusual events. They're a fundamental part of how galaxies evolve and grow over cosmic time. In the early universe, shortly after the first galaxies formed, mergers were extremely common. Small proto-galaxies containing just millions or billions of stars constantly collided and merged, gradually building up larger structures. Our own Milky Way is the product of countless such mergers. Astronomical observations and computer simulations suggest that the Milky Way has consumed dozens of smaller galaxies throughout its history. We can see evidence of these past mergers in stellar streams and disrupted dwarf galaxies currently being torn apart by our galaxy's gravity. Andromeda has a similar history. It too has grown through mergers and cannibalization of smaller galaxies. What we're witnessing with the Milky Way-Andromeda collision is simply the next chapter in this ongoing story of galactic evolution. It's not unique. It's not special in any cosmic sense. Similar mergers are happening throughout the universe all the time, in galaxy clusters, where large galaxies are packed relatively close together. Mergers are even more common. Over billions of years, multiple large galaxies in a cluster can merge, eventually forming a single giant elliptical galaxy at the cluster's centre. These giant ellipticals can contain trillions of stars, far more than either the Milky Way or Andromeda. They're the most massive galaxies in the universe, and they're all products of mergers. Our merger, the creation of Milky, is just one of countless such events occurring across cosmic history. And here's something that gives the merger an even broader context. We can observe galaxy mergers in various stages throughout the universe. Telescopes have captured images of galaxies currently in the process of merging, frozen at different points in the collision sequence. Some images show two galaxies just beginning to interact, their spiral structures still intact but with tidal tails just starting to form. Others show galaxies in the midst of violent encounters, their structures completely disrupted, stellar bridges connecting them, vast plumes of stars streaming into space. Still others show nearly completed mergers, systems where two galaxies have combined into chaotic, irregular structures not yet settled into their final forms. By studying these systems, by observing mergers at different stages frozen in time, astronomers have pieced together a detailed understanding of how galaxy mergers proceed, what happens during each phase, what the final products look like. These observations confirm what computer simulations predict. They show that mergers of two large spiral galaxies typically produce elliptical galaxies. They show that mergers trigger starbursts, periods of intense star formation. They show that stellar collisions are rare even during violent mergers. They show that significant fractions of stars can be ejected into intergalactic space. Everything we predict for the Milky Way-Andromeda merger is based on both theoretical models and direct observations of similar mergers elsewhere in the universe. We're not speculating, we're extrapolating from observed phenomena, and the agreement between theory and observation gives us confidence that our predictions for Milky are reliable, at least in broad strokes. The details might vary. The exact timing might be off by hundreds of millions of years. The precise structure of the final merged galaxy might differ from what models predict. But the overall narrative, the general sequence of events, is well established. Think about what it means that we can predict events billions of years in the future with any confidence at all. Humanity has existed in anything resembling its current form for maybe 200,000 years. Civilization, agriculture, cities, writing, all the things we consider fundamental to human society, have existed for maybe 10,000 years. Science as we know it, the systematic investigation of nature through observation and experiment, is only a few hundred years old. And yet, with just a few centuries of scientific progress, we can peer billions of years into the future and say with confidence, this will happen. These two galaxies will collide. They will merge. This is what the result will look like. That ability, that power to understand cosmic processes on timescales, utterly dwarfing human experience, represents one of the great triumphs of human intellect. We're ephemeral creatures living on a tiny planet orbiting an ordinary star in an ordinary galaxy. Our individual lives last mere decades. Our civilizations, even the longest lasting ones, persist for mere thousands of years. But we can understand and predict cosmic events spanning billions of years. We can grasp the deep time of the universe, can follow the causal chains connecting present observations to distant future outcomes. And yet, despite this understanding, despite our ability to predict Milky's formation, we remain fundamentally powerless to affect it. There is nothing anyone could do, no technology we could possibly develop that would prevent or alter this collision. The masses involved are too enormous, the energies are too vast, the gravitational forces at play are beyond any conceivable engineering intervention. Even a civilization millions of years more advanced than ours, with technology that seems like magic from our current perspective, would be unable to stop two galaxies from merging. You can't just push a galaxy out of the way. You can't alter its trajectory. The mass scales involved make any intervention absurd. It would be like an ant trying to alter Earth's orbit around the Sun by pushing on the ground. The disparity between the ant's capabilities and the scale of the task is similar to the disparity between any imaginable civilization and the task of preventing a galaxy merger. So the merger will happen. It's inevitable, already in motion. The only question is whether anyone will be around to witness it. Will humanity, or our descendants, or our creations, survive long enough to see Andromeda's arrival? Will we persist for 4.5 billion years? That's a time span almost incomprehensible from our current perspective. For context, complex multicellular life has only existed on Earth for about 600 million years. 4.5 billion years from now is more than 7 times longer than the entire history of complex life to date. The challenges facing any species trying to survive that long are staggering. Natural extinction events, asteroid impacts, supervolcanic eruptions, climate changes, ice ages, all the natural disasters that have caused mass extinctions in Earth's past will continue occurring. Any species remaining on Earth faces inevitable extinction from natural causes if nothing else gets them first. And then there are the longer-term existential threats. The Sun's increasing luminosity will make Earth uninhabitable in about 1 billion years. Any life still on Earth at that point will need to either adapt to extreme conditions, migrate to other worlds, or go extinct. If humanity or our descendants survive, they'll need to become a multi-planetary species, spreading to other star systems, establishing new homes around other stars. Only by spreading across multiple systems can a species hope to survive for billions of years. Even then, the challenges are immense. Stars die. Planetary systems become unstable. Cosmic disasters like nearby supernovae or gamma-ray bursts can sterilize entire regions of a galaxy. Surviving for billions of years requires not just spreading across space, but continually adapting, migrating, finding new homes as old ones become uninhabitable. If we do survive, if some form of humanity or post-humanity persists across those unimaginable spans of time, what would it mean to witness the merger? Not just to observe it happening, but to live through it, to experience multiple passes of two galaxies interpenetrating, to watch the sky transform over millions of years as the merger progresses. It would require a continuity of civilization, of memory, of purpose that seems almost impossible to imagine. Our oldest continuous civilizations have existed for maybe 5,000 years. The merger will take place across timescales millions of times longer. Maintaining any sort of cultural continuity, any consistent identity or purpose across such durations, would require forms of social organization and information storage completely unlike anything we currently possess. Perhaps by then, if anyone still exists to witness the merger, they won't be biological at all. Organic life, constrained by evolution's slow pace and biology's fragility, might seem hopelessly inadequate for surviving cosmic timescales. Perhaps consciousness will have migrated to artificial substrates, to computational systems that can persist indefinitely, backing themselves up, repairing damage, migrating from failing hardware to new hardware as needed. Digital entities could potentially achieve something approaching immortality, at least until the universe itself becomes hostile to computation. They could witness the merger not as brief-lived individuals, but as continuous consciousnesses persisting across the entire duration of the event, remembering the first approach, experiencing each pass, watching the final merger, and continuing onward into Milkywe's future. Or perhaps consciousness will have transcended even digital form, finding ways to encode information and experience in the structure of space-time itself, or in exotic forms of matter we haven't yet discovered, or in dimensions we don't currently perceive. Speculating about what's possible across billions of years of technological development quickly becomes futile. We're trying to imagine capabilities that might be as far beyond our current understanding as modern quantum physics and genetic engineering would be to Paleolithic humans. The gap is too large, the time span too long. All we can say with confidence is that if anything recognizably descended from humanity witnesses the merger, it will be transformed beyond anything we can currently conceptualize. But there's another possibility, perhaps the most likely one. Maybe nobody will witness the merger. Maybe the universe, at that point in its history, will be completely devoid of observers, not because of some catastrophic extinction event, but simply because maintaining technological civilization across billions of years might be fundamentally unsustainable. Every civilization that has ever existed on Earth has eventually collapsed. The Romans fell, the Egyptians faded, the Maya disappeared. No political structure, no empire, no nation has proven permanent. They all rise, flourish for a while, and inevitably decline and fall. What makes us think galactic civilizations would be any different? Perhaps there are fundamental limits to how long any organized system can persist before succumbing to entropy, to internal conflicts, to resource depletion, to simple existential exhaustion. Perhaps life itself has inherent timescales beyond which it cannot persist. Even if a species spreads across multiple star systems, even if it achieves something approaching biological or digital immortality for individuals, perhaps there are limits to how long populations remain viable. Maybe accumulated genetic damage, or accumulated errors in digital substrates, or simple thermodynamic constraints set ultimate limits on longevity. Maybe every species, every form of life or artificial life, has a natural lifespan measured in millions or billions of years, after which it inevitably fades, leaving behind ruins and artifacts that persist for a while before they too dissolve into the background radiation of the cosmos. If that's true, then the merger will proceed unwatched, unobserved, two galaxies colliding in a universe devoid of minds to comprehend what's happening. And honestly, that's fine. The universe doesn't need observers. It doesn't require consciousness to witness events for those events to have meaning or significance. The merger will happen regardless of whether anyone watches. Stars will be rearranged. New stars will form. Old stars will die. A new galaxy will emerge from the collision. All of this will occur according to the laws of physics, following the inexorable logic of gravity and motion and thermodynamics, completely indifferent to whether consciousness exists anywhere in the universe to observe it. The cosmos operated for billions of years before life emerged on Earth. It will continue operating for trillions of years after Earth is gone, after the Sun dies, after the Milky Way and Andromeda have merged, and Milkomeda itself has aged into senescence. The universe doesn't need us. It never did. That thought should be humbling, but it shouldn't be depressing. There's something clarifying, something almost liberating about recognizing our cosmic insignificance. We're not the center of the universe. We're not the point of creation. We're not the reason any of this exists. We're a temporary pattern in the flow of energy and matter, a brief local decrease in entropy sustained by burning through the sun's energy, destined to dissipate eventually as all such patterns do. But that doesn't make us meaningless. It doesn't render our experiences invalid or our struggles pointless. It just means that meaning and value are things we create, not things the universe provides. We assign significance to our lives, our relationships, our accomplishments, our experiences, and that self-created meaning is no less real for being self-created. The merger of the Milky Way and Andromeda is a cosmic event of staggering scale, but it's not unique, it's not even particularly unusual. Similar mergers have happened throughout cosmic history. They're happening right now in distant parts of the universe. They'll continue happening for as long as galaxies exist. In the very distant future, trillions of years from now, when cosmic expansion has separated remaining galaxy clusters by such vast distances that they can no longer see each other, when each cluster has merged into a single giant elliptical galaxy, even those mergers will cease. The universe will enter an era of profound isolation, with galaxies so far apart that they're completely causally disconnected from each other. But that's so far in the future that it makes the Milky Way Andromeda merger seem imminent by comparison. For now, for the foreseeable future, at least in terms of timescales humans can comprehend, the merger is distant. It's billions of years away. It has no practical relevance to our lives, to our civilization's near-term challenges, to anything we'll experience across the next thousands or even millions of years. Climate change, asteroid impacts, nuclear war, pandemics, artificial intelligence risks, all the existential threats facing humanity operate on timescales of years to centuries, maybe millennia. The merger operates on timescales of billions of years. By the time it becomes relevant, every problem we currently face will be long resolved or long past mattering. Humanity will either have survived and thrived and spread across the stars, or will be extinct, just another failed experiment in evolution's long history of trial and error. But even though the merger is distant, even though it has no practical impact on our lives, there's value in contemplating it. There's value in confronting the true scale of the universe, the deep time over which cosmic processes operate, the vast indifference of the cosmos to human concerns. It provides perspective. It reminds us that our problems, as urgent as they feel, as important as they genuinely are to us, are tiny blips in the cosmic story. Empires rise and fall. Species emerge and go extinct. Planets form and are destroyed. Stars are born and die. Galaxies collide and merge. And through all of this, the universe continues, utterly indifferent, following the laws of physics wherever they lead, generating complexity and structure and pattern and life, allowing brief pockets of order to emerge temporarily before dissolving back into entropy's slow march toward equilibrium. Understanding this, really internalizing it, changes how you see the world. Petty concerns start to feel petty. Long-standing grudges seem pointless. The things we spend so much time worrying about, status and reputation, and material possessions and social standing, all of it feels trivial when measured against cosmic scales. This doesn't mean those things don't matter at all. They matter to us, and we're entitled to care about them. But recognizing their cosmic insignificance provides useful perspective. It helps distinguish between things that are genuinely important, things that affect well-being and flourishing and suffering, and things that are merely arbitrary social constructs we've collectively agreed to care about. And there's something profound about the fact that we, ephemeral creatures living brief lives on a tiny planet, can understand any of this at all. We can look at a faint smudge of light in the night sky and know that it's another galaxy. 1 trillion stars arranged in a spiral, racing toward us at 110 kilometers per second, destined to collide with our galaxy in 4.5 billion years. We can predict what will happen during that collision. We can model the physics. We can run computer simulations that show us what the sky will look like at various stages of the merger. We can trace the histories of both galaxies backward, billions of years, to their formation in the early universe. We can project their futures forward billions of years to the final merge structure. We possess this cosmic perspective, this ability to step outside our immediate experience and comprehend the universe on its own vast scales. That ability is recent. For most of human history, for hundreds of thousands of years, we had no idea what stars were. We didn't know the Earth was a planet. We thought the sun revolved around the Earth. We believed the universe consisted of Earth and the heavens, with everything visible rotating around us on celestial spheres. The idea that Earth was just one planet among many, that the sun was just one star among billions, that our galaxy was just one galaxy among trillions, all of this understanding has developed within the last few hundred years. The timescale of our ignorance dwarfs the timescale of our knowledge. And yet, despite possessing this knowledge for such a brief period, despite being such recent arrivals at understanding cosmic truths, we've managed to piece together a remarkably accurate picture of the universe's structure, history, and future. This knowledge comes at a cost, though. Ancient humans lived in a smaller, cozier universe. The cosmos had a human scale. Earth was the centre. Humans were the point. The gods cared about human affairs. Everything had meaning and purpose within a comprehensible narrative. We've traded that comforting smallness for a universe of almost incomprehensible vastness, where we're not at the centre, where we're not the point, where no gods watch over us, where the cosmos operates according to indifferent physical laws that care nothing for human hopes or fears or dreams. Some people find this trade devastating. They experience existential despair when confronting cosmic insignificance. The universe's vastness and indifference feels crushing, unbearable, void of meaning. But it doesn't have to feel that way. You can find the universe's scale inspiring rather than crushing. You can appreciate that we're part of something vastly larger than ourselves, that we're brief participants in a cosmic story that extends billions of years into the past and will continue billions of years into the future. We're made of stardust quite literally. The atoms in your body, the carbon and oxygen and nitrogen and iron, were forged in the cores of stars that lived and died billions of years ago. Those stars exploded as supernovae, scattering their enriched material into space. That material eventually coalesced into new stars and planets, including our Sun and Earth. The atoms that make up your body have been cycling through the universe for billions of years, incorporated into countless structures before becoming temporarily arranged in the pattern that is you. And after you die, after your atoms are returned to the environment through decomposition or cremation, they'll continue cycling. They'll be incorporated into other organisms, other structures, other patterns. Some might eventually leave Earth entirely, escaping the planet's gravity and drifting into space. Others might remain on Earth until the sun's expansion vaporizes the planet billions of years from now. Either way, your atoms will persist. They'll outlast human civilization. They'll outlast Earth. They'll survive the merger of the Milky Way and Andromeda. They'll still exist in Milkomeda, scattered among the trillion stars of that merged galaxy, continuing their cosmic journey through structures and forms we can't begin to imagine. There's a strange comfort in that continuity. You're temporary, but the substance of you is ancient and will persist long after you're gone. You're a temporary arrangement of ancient stardust, animated by chemical reactions and electrical signals, self-aware for a brief moment, experiencing the universe from one tiny perspective, then dissipating back into the raw materials that will form future structures. This is true for everyone. Every human who has ever lived, every animal, every plant, every microorganism, all of us are temporary patterns in the flow of matter and energy through the universe. We emerge briefly from the cosmic background, experience existence for a while, then dissolve back into that background. And that's okay. That's how it should be. Permanence would be a curse, not a blessing. The merger of Andromeda and the Milky Way is a reminder of impermanence operating on the larger scales. Galaxies, those vast cosmic structures containing hundreds of billions or trillions of stars, structures that seem eternal and unchanging from our brief perspective, are temporary too. They form, evolve, merge, and eventually fade. In the extremely distant future, tens or hundreds of trillions of years from now, even galaxies will die. Their stars will exhaust their fuel and fade. New star formation will cease once available gas is consumed. The universe will enter an era dominated by stellar remnants, white dwarfs, neutron stars, black holes, all slowly radiating away their energy into the cold darkness of an ever-expanding cosmos. Eventually, even black holes will evaporate through Hawking radiation, a process so slow that it takes 10 or 100 years or more for the largest black holes. But eventually it will happen. And then the universe will contain nothing but a thin soup of elementary particles at temperatures infinitesimally above absolute zero, everything settled into maximum entropy. No structure, no complexity, no life, nothing but equilibrium. That ultimate fate is so far in the future that it's almost meaningless to contemplate. The time from the Big Bang to now, 13.8 billion years, is essentially zero compared to the time until heat death, which is measured in numbers so large they require exponential notation to write down. But it's worth mentioning because it emphasizes that everything is temporary. The universe had a beginning. It will have an end. Or at least it will evolve into a state so different from the current state that calling it an end seems appropriate. Between the beginning and the end, structures form and dissipate. Complexity emerges and dissolves. Life appears and goes extinct. Consciousness arises and fades away. All of it temporary, all of it contingent, all of it ultimately doomed by entropy's patient march toward equilibrium. And yet, here we are, in this brief window of cosmic time when structure exists, when complexity is possible, when stars burn and planets orbit and life emerges and consciousness develops, and beings can look up at the night sky and wonder what it all means. We're extraordinarily fortunate to exist in this era. If we'd emerged just a few billion years earlier, when the universe was still mostly hydrogen and helium, before generations of stars had produced the heavy elements necessary for complex chemistry, life as we know it would have been impossible. If we emerge billions of years in the future, when star formation has ceased and the universe has grown cold and dark, life would be equally impossible, at least carbon-based life dependent on stellar energy. We exist in a sweet spot, a narrow window of cosmic time when the universe is old enough to contain the necessary chemical elements, but young enough that stars still burn and provide energy for life. That window is temporary, but it's still incredibly long by human standards. Stars will continue burning for trillions of years. New stars will continue forming, albeit at ever-decreasing rates, for perhaps another 100 trillion years or more. Life, if it continues to exist and spread, has plenty of time remaining. The merger of the Milky Way and Andromeda, as dramatic as it is, represents just one relatively minor event in that long future. Milky will be a perfectly good galaxy for hosting life and civilization, assuming anyone still exists to take advantage of it. The stars in Milky will continue shining. Planets will continue orbiting those stars. Habitability will persist. The merger doesn't end the story, it's just another chapter. So what should we take away from all this? What does it mean that two galaxies are on a collision course? That they'll merge billions of years from now? That the process will transform both beyond recognition? That the resulting galaxy will eventually age and fade like everything else in the universe? Perhaps the message is simply this: impermanence is universal. Nothing lasts forever. Everything that exists will eventually cease to exist, at least in its current form. Galaxies merge and fade. Stars die. Planets are destroyed. Species go extinct. Civilizations collapse. Individual lives end. All of it temporary. All of it transient. All of it subject to time's relentless forward march. But impermanence doesn't negate value. The fact that something is temporary doesn't make it meaningless. A sunset is beautiful despite lasting only minutes. A piece of music is moving despite ending. A relationship is meaningful despite not being eternal. We don't dismiss these things because they're temporary. We appreciate them partly because they're temporary, because we know they won't last, because their transient nature makes them precious. The same principle applies on cosmic scales. The universe's temporary structures, its galaxies and stars and planets and life, are no less remarkable for being temporary. If anything, their impermanence makes them more remarkable, not less. The Milky Way and Andromeda are ancient structures, billions of years old, containing trillions of stars between them, hosting uncountable planets, possibly numerous instances of life, maybe even multiple technological civilizations, And in 4.5 billion years, they'll collide. Their structures will be disrupted. Their spiral forms will be destroyed. They'll merge into something new, something different, something that won't resemble either progenitor. And eventually, billions of years after that, even Milky will fade. Its stars will die. Its structure will dissolve. The atoms that currently make up both galaxies will be scattered across vast regions of space, some incorporated into new structures if any still form, others drifting in isolation through the expanding void. Nothing about either galaxy is permanent, but that doesn't diminish their magnificence. It doesn't reduce their significance as structures that arose from simpler matter, that self-organized through gravity's patient work across billions of years, that created environments where stars could form and planets could exist and life could emerge. When you look up at Andromeda tonight, if you can find a dark enough location away from city lights, that faint smudge you see represents 1 trillion stars arranged in a spiral structure 220,000 light-years across, located 2.537 million light-years away, approaching at 110 kilometers per second. The light entering your eyes left those stars 2.37 million years ago. It crossed the vast intergalactic void while humanity evolved from primitive hominids to the species we are today, and it will continue approaching. Andromeda will grow larger in Earth's sky over the coming millions and billions of years, assuming Earth still exists and anyone is around to observe it. The merger will proceed exactly as physics dictates, indifferent to observation, operating according to gravitational principles that care nothing for human hopes or concerns or existences. And that's okay. That's how it should be. The universe operates according to laws, not whims. It follows mathematical principles, not narratives. Gravity doesn't care about creating dramatic stories or meaningful lessons. It just attracts mass to mass according to the inverse square law. But from that simple principle, from gravity's patient work across cosmic time, extraordinary complexity emerges. Galaxies form, stars ignite, planets coalesce, life arises, consciousness develops, and beings that are themselves temporary, arrangements of stardust, can look up at the night sky, observe distant galaxies, understand the physics governing their motions, predict their futures billions of years ahead, and feel connected to something vastly larger than themselves. That connection is worth preserving. That perspective is worth maintaining. In our daily lives, we're necessarily focused on immediate concerns, on problems and challenges and opportunities operating on human timescales. That's appropriate. Those concerns are real and important. But occasionally it's worth stepping back, looking up at the night sky, finding that faint smudge of light in Andromeda's constellation, and remembering that's another galaxy, 1 trillion stars, approaching us, destined to merge with our own galaxy billions of years from now. The scale is incomprehensible. The time scale is unimaginable. The indifference of the cosmos to human concerns is absolute. And yet we can understand it. We can measure it. We can predict it. We can appreciate it. And in that appreciation, in that moment of cosmic contemplation, we connect with something larger, something more enduring, something that places our brief lives in context, not to diminish them, but to remind us that we're part of a story that extends far beyond our individual experiences, far beyond our species, far beyond our planet, into the deep time and vast scales of the cosmos itself. The Milky Way and Andromeda will merge. Milky will form. Eventually that galaxy too will fade and die. The universe will continue evolving toward its inevitable equilibrium, and through all of it, whether or not consciousness persists to observe it, the cosmos will remain magnificent, operating according to physical law, generating temporary pockets of complexity and order, allowing brief moments when structure emerges from chaos before entropy reclaims everything. We're fortunate to exist during one of those moments. We're fortunate to possess the ability to understand, even partially, the cosmic processes that govern our existence. And we're fortunate to live in a time when we can look up at the night sky and see Andromeda, knowing what it is, understanding where it's going, appreciating both its current beauty and its future inevitability. That knowledge, that perspective, that cosmic awareness is one of humanity's greatest achievements. It deserves to be celebrated, contemplated, and preserved for as long as we persist as a species. Because when you understand the true scale of Andromeda, when you grasp the full implications of the coming merger, when you internalize the deep time across which these events unfold, everything changes. Your perspective expands. Your concerns are contextualized. Your life, brief as it is, becomes part of a larger cosmic story. And that story, though ultimately temporary like everything else in the universe, is magnificent beyond words.